So good afternoon, everyone. Welcome back to Math 122. Back first day after the exam. So today we're going to continue our discussion of Chapter 2, where we're finally starting to get our hands on some actual calculus topics. So today we're going to cover Section 2.4, and if we have time, then we'll get to Section 2.5, but I'm not particularly worried about it. Regarding your homework, you have homework assignments which are due on certain days, and they can be seen on the screen here. So 2.3 is due on February 27th. That's Monday, I think. And then 2.4 is due March 1, 2.5 due March 3. So I guess that's Monday, Wednesday, Friday of next week. That's the homework schedule. Your next assessment is going to be quiz, I think it's quiz 5. And that'll be on Thursday of next week, which is March 2, right?
Yeah.
Okay, thank you. So that's your next quiz, is going to be March 2. So the content for the quiz is going to be 2.2, 2.3, and 2.4, because those are all the homework assignments that are going to be due in between the last exam, which covered everything up to 2.1. Okay? So that's going to be your next quiz. Regarding studying for that, you can come to my office hours at the usual time, Math Tutoring Center at the usual time, or the SI sessions with Jacob, or you can go to any of the other SI sessions elsewhere. So are there any administrative questions before we start in on content today? All right, like I said, I'll try to have those exams graded by the end of the week, by which I mean I'll put them in by like Friday evening. All right, so let's return to what we were talking about before, and I want to say a little bit more about this tangent line stuff before we move on to 2.4. So generally in Chapter 2, we've been talking about this notion of derivatives, okay, or instantaneous rate of change, which tells us, okay, how a function is changing. And I like to come back to this picture because this was sort of how we learned how to figure out what is the slope of a curve as opposed to a slope of a line, right? So a slope of a line, we can just do rise over run. But for curves, we have different steepness at different places. So one thing that we learned early on was how to do average rate of change, i.e. find the slope of the secant line that passes through 2 points. But if we want to know what is the slope of the function at a point, what we can do is we can take this slope of the secant line over smaller and smaller intervals, closer and closer to the point, and that can give us an idea of what is going to be the actual slope of the tangent line. And the actual slope of the tangent line is what we call the instantaneous rate of change of f at a, or we call it f prime of a, okay? So it's a number which represents this slope of this tangent line. And you can kind of think of it, what I like to draw sometimes is like, if you imagine that you're riding on the purple line as if you were on a roller coaster, okay, what would you look like? You'd look like this. Here's you. Okay, and depending on where you were on the roller coaster, you might be facing up, okay, as in pitched up, right, if you're going up a hill, or you might be facing down, right? And how steep that part of the curve is sort of characterized by the steepness of this tangent line here, okay? So this is telling us like how steep the curve is at a point. Okay, so that was derivatives, and then let's see, what did we learn after that? Then we learned what it means for the derivative to be positive or to be negative, right? If the derivative is positive, then that means the slope of the tangent line is positive, i.e. if I'm riding my roller coaster, I'm going up. Okay, from left to right, I'm going up. Or if the derivative is negative, then I'm going down, right? Okay, so what else was there? So next up, we learned a little bit about the derivative function and the fact that, in fact, we can actually graph the derivative function. Okay, so we can find all of the numerical values of the derivative, i.e. all of these slopes of all of these lines, okay, at every single point, and then we can find out, well, what does the picture look like if I graph that function, okay? So that function's job is to take as an input the x value, And what should it output? What it should output is the slope of the tangent line to the function at that point. Okay? So the function tells us the height. The derivative tells us the steepness of the parent function. Okay, so then we had Leibniz notation, different way of writing derivatives, and then we sort of started talking about this tangent line approximation. So before we jump back into tangent line approximation, are there any general questions about chapter 2 so far regarding just like derivatives, what they are, how we graph them, and the connection between the derivative and like increasing and decreasing and constant? Okay, then I'm going to talk for a little bit about tangent line stuff, and then I'm going to talk, well, yeah, and then we'll do an example. How about that? We'll have a little bit of group work, I think. Okay, so what was tangent line approximation? Well, we said that we can draw this tangent line to a function at a given point, okay, and if x minus a is small. So what does this mean? If the x value we are choosing, which we are free to choose, is close to the x value which characterizes this tangent line, okay, so namely, if we're not too far away from the point at which the tangent line touches the function, then what is going to be true? Then the function value is going to be similar to the tangent line value, meaning the height of the tangent line will be similar to the height of the function. And you can see that in this pink region here, okay? If I wanted to guess what is the height of this black line, which goes from x up to the green curve, okay? It's not that different than the height of the orange dashed line, which goes from the x-axis up to the blue line, okay? So that's what tangent line approximation is. Okay, so let's see how we actually do it. Well, in order to do it, what we need to have is a formula for the tangent line, okay? A formula for the tangent line. So that's what we're going to talk about really quickly. So the equation of the tangent line, which we talked about last time, which we call this tangent line t of x, t for tangent, to f of x at x equals to a, is given by this formula. So t of x is going to be equal to f of a plus f prime of a times x minus a. Okay, so that's a little bit confusing, but let me show you where that equation actually comes from. So let's do this example where we just take f of x equals to x squared. And we're going to take our a value to be some positive number. And we want to know what is the equation of the tangent line, i.e. what is the equation of this pink dashed line. Okay, well, what are the two things that I need in order to find the equation of a line? Someone help me out with one of them.
The y-intercept.
Y-intercept and slope, or slope and a point. Okay, so if we have the y-intercept, that's a specific point, but we really just need a point plus the slope. Then we'll know what is the equation of this line. Well, I know that the slope of this line is f prime of a, the derivative, right? And I also know that it passes through the point a comma f of a because it touches the graph of f of x when x is equal to a. So if I use point slope, okay, I can put this equation together in the following way. So I know that y is equal to t of x, so I'm going to replace y by t of x, and then I'm going to subtract y1, which is the height of the point. Okay, so minus f of a is equal to the slope, which is f prime of a, times x minus, and the x1 is the specific x value, which we are choosing to be a in this case. So we can derive this formula, which if we just move f of a over to the other side, we get t of x equals to f of a plus f prime of a times x minus a. Okay? So the two things that you need to know in order to make this formula, or I guess three things, the three things are you need to know what A is, you need to know what f prime of A is, and you need to know what f of A is. So later on, we'll have some more robust methodologies for coming up with what f prime of A is. For now, if I ask you to find the equation of the tangent line, I will tell you what that number is. Okay, so let's do it for f of x equals x squared. What would it look like? Well, I know I'm going to tell you that, well, we can figure out what f of, let's say A is equal to 2 for now. So let's say f of 2, we can get that by just doing 2 squared, so that's 4. And then f prime of 2, I'm going to tell you is equal to 4. I'm telling you that the slope of this pink line is 4. Well, we can make the equation of the tangent line by just plugging in these values. I know that A is equal to 2, so I have f of 2, f prime of 2, and A is equal to 2. So t of x, in this case, is going to be equal to 4 plus 4 times x minus 2. And now maybe this is a little bit more familiar to you as like the equation of a line. Okay? So, for example, if I wanted to know what f of 1.1 is, without actually squaring it, then I could do the following. I could do 4 plus 4 times, okay, not equals, sorry, but is approximately equal to 4 plus 4 times, sorry, not 1.1. Man, I'm tripping all over my feet here. I meant to say 2.1, okay? So 2.1 is an x value which is pretty close to 2, and I'm guessing that the height of the function is pretty close to the height of the tangent line. So let's see if that's true. I'm going to approximate this by 4 plus 4 times 2.1 minus 2, which gives me 4 plus 4 times 0.1 is 0.4, so 4.4. Okay, well, what would we get if we actually did f of 2.1? Well, we would get 2.1 quantity squared. Someone have their calculator who can do that for me? (2.1 squared) 4.41. Okay, great. So it looks like our approximation was pretty close, right? And we expected that to be true because the height of the tangent line will be similar to this function at this point. Okay? Any questions on this so far? Okay, then we're going to do a quick group work exercise. Oh yeah, sorry. Still writing? All good now? Okay. So we're going to do a quick group work exercise so that you guys can get your hands on this yourselves. Okay, so we're going to try this problem 3 in a group. Okay, so we've got fertilizers doing something. Okay, and we have a function here. We know the function value and we know the derivative value. And we're going to try to use our tangent line, okay, to approximate what is the actual function value. So you might find it helpful for your group if you draw a picture of what's going on. And you'll work on these and I'll be coming around. And actually Jacob will also be coming around today to help if you need a little bit of help. So Jacob, you want to take that side of the room today? All right, sweet. Go ahead and get started.
I'm still trying to figure out A.
Oh, Oh, yeah, we gotta interpret this. I do. Let's try to just put that straightforward. Okay, so I'm now I've already got enough. I've already got enough. Did I set this up again?
Okay, well, A is just asking you to interpret the statements F of 5 equals 1,000. But for B, yeah, you're on the right track, right? We're gonna put F of 5 in for F of 5, and F prime of 5 in for this. But then what's gonna be different when we're doing F of 6 and F of 10? Okay, that means that our X value is going to be either 6 or 10. So that's exactly what we're gonna put right here.
Or is it 5 shillings for?
It's definitely 5 kilograms of fertilizer.
5 kilograms of fertilizer.
And then it just,
Yeah, okay, so 5 grams of
well,
fertilizer.
it's like $11,500 shillings from the yearly fees.
Okay, so 5 kilograms produces 11,500 shillings. Whatever.
Yeah.
Okay, I interpreted the shit out of that.
I don't know what the F5 is.
So, prime
So when I write F of 5
It would be like 350 shillings per kilogram.
That's what I was thinking, but I don't. I'm not smart. I mean, does that work out? How does that work? I'm not good at math, so.
It's tough to actually.
It's definitely not how the calculations work. Act like it is, and then when he says that it isn't, then you're like, oh my god, I knew that. Okay, anyways, it's fine. I can plug all this together. So that means 5 kilograms of fertilizer and 11,500 plus 350. And then like doing a 5.1 minus 1. Something like that.
F prime.
I support this. I approve of this method. Something happens after this.
The slope, right? Which the slope how the okay, so let's just say look, increase our fertilizer used. Do you think that the price is going to go up or down? It's going to go up. And in fact, we know kind of roughly speaking how quickly the price goes up.
The banana thing. I don't like this.
Look at this feels right. Sorry, we're giving you.
No, you think you're mad. I can read all the time. Something is not horribly wrong in the process. But like,
I just took that
what'd you plug in for X?
like 6 or 10. Because there are X's. F of X equals 6.
Yeah. But oh yeah, you're right. Wait, I did this one. Hold on. Okay, never mind. I'm skipping.
Here first. Yeah, exactly. So the F function, right?
quite goofy.
Yeah. Very aggressive. So
Adjustment would be definitely okay, I said that.
So it's 3
I don't know, he finished that shit in like 25.
No, I know. You like walked out there, but I was staring because I was staring at what the lecture, but I didn't know how much more I could simplify it, and I just couldn't. And I stared at it for like 10 minutes.
I was like, oh, this was fun. So maybe I'm just low key achieving.
okay, so we have to be careful with the
I'm so sick.
Oh, you know the cat before. Let me draw the FFA.
Stop.
So our function may not
I
necessarily.
told my brain to like snap out of it because I thought that it would work.
Well, I'm glad that you tried that because that's not
The one that's close to the
First thing
No,
is
it sounds like
at that
my
prime
throat
thing,
is
so
just
by 5 kilograms times the cross 11,000.
like it's just like that, like it's one of those like off sort of thing. It's not off.
F prime of
So it's
5
zero to
is
1, my throat tickles, and I'm like,
that's representing the slope of
it's like I got it.
okay, which is telling you roughly speaking how quickly is the price increasing as we move away from 5 kilograms.
A lot of my friends are like,
Roughly speaking, like how much is the next kilogram going to cost? But a 6 kilogram,
I'm trying to like dodge it. I don't know if I like dodge it or
something like that. It's not necessarily a like so it just tells you like how quickly the price goes up from so it's sort of a local thing.
I gotta do laundry, homework.
So
I'm literally
basically, yeah, that's what we're gonna do.
Going
So
to
if you
jump
think
off
about
the
this
top of
point,
the
right, f of 6 is approximately t of 6, which is f of 5 plus f prime of 5.
Do you live at East One?
We put in 6 for x.
at 5.
6 minus 5 is
Do you
1,
know
which means
anybody
this
was
equation
even like
reduces to
Will Mahaffey, Iron
500
Player,
plus
Cummers,
3.
I probably
525 is there?
Oh, I'm not on
Exactly
that.
what you said.
Like I saw, like I
I was
probably
gonna
met
say,
him.
they're horrible people, they love
I've probably like met them.
That's so funny.
It's crazy too because I know how to get on the top of East Bar. I could go up and jump off that. Dude, no, I could. Like, hold up. I got so many videos.
5 if you're doing it far away, but here's the deal. That's going to give you the height of
Bro, what?
this point over here. But depending on what this function looks like, these
How do you
things
get
get
up there?
quite
There's like a ladder that puts you inside, like where like
going further away is
like type spaces, and then there's like a ladder going up into this floor at the very top, and you climb up, and there's like these like you're walking on like plywood, and they're hanging off of the slope. It's sketchy as hell. It's so funny. Every time I go up there, it's not a great idea. But like, I did get some dope bets for you. So. The trade-off is, you know, fall off of East Squad, which way to go on. You know, my B-reel looked sick. Splattered myself on it.
Yeah, so you're just going to use the equation that he just went over. So the f of a is going to be the f
Floor 5 of East Squad.
So you'll have the
It's like a Twilight
11,500.
It's so much crazy shit.
The f prime of
Like
a,
every night there's just some mind-boggling stuff.
and then x minus a,
It's just like,
which is
so strange.
6 minus 5.
Like I hear about like what everybody else does in the army, and I'm like, man, it's not
Do the same thing with
fucking
x
boring.
Yeah, Patterson. So boring.
I know, I've been there a few times, bro, and I'm just like, nobody like comes out.
No.
Like,
Yeah, because you're
like
using
everybody's always out in the hallways doing some
That's
shit. Like,
that's
people
what
are
you
home
do
and
to estimate.
Yeah, no, I tried. I played tennis in the
10 minus
fall.
5.
And that was fun. That was like a big one of the year.
We do like the hallway golf. We have just
Now my like entire floor hates me because I don't play tennis at all.
5 plus
There's like girls in the hallway who like whenever the golf ball went at their door, one of them would come out and all of their roommates would hate her. So like she's just like universally hated by everybody, but it's always her versus the world. I swear. Like the one night she was like trash and she came out yelling about some bullshit and just like screaming at party. I'm like,
and they're
just
changing
like
out
chill. Like
350.
just like do something.
If they keep changing in the same way, okay,
That's what I'm
and
saying,
price is
bro.
6 here.
But like
This
this
number
was
will
just
be
some
1.
stupid shit.
This number is 350.
Like the other night, bro, like our room, there's so much like traffic through our room, everybody comes to our room.
Yeah.
And like, it's like 4 a.m. And like, these random girls came in and started playing like just random fucking music, like a crazy song. They played like Cupcake, and then they played like Wheels on the Bus, they're playing like Halloween, but they're just like dancing. And I was just like sitting there baffled. I'm like, I'm tired of shit.
Also,
Like, just like random stuff is always happening. Like I told you, we shaved our
yeah, I got it. It's kind of weird.
That's actually hilarious.
It's approximately equal things. This might be one of the first times you sort of see this approximation thing. So
There's just always something dumb as shit going on.
Okay, do we want a little bit more time to work, or are we all right? Okay, let's talk about it as a group. I saw some good work out there. So, someone help me with the interpretation. What does f of 5 equals 11,500 mean in terms of this problem? Yeah.
That means that for 5 kilograms of fertilizer, that they get 11,500 kg.
Yeah. 5 kilograms costs 11,500 shillings. Okay, good. And how about f prime of 5 equals 350? Who thinks that one was harder to understand? Yeah, it's trickier, right? But what does the derivative represent? It represents how a function is changing. If a function is changing, okay, regarding cost, it's referring to the rate at which the cost is increasing. One way you can see that is ask yourself, what are the units? The units of the derivative function are the units of the function divided by the units of the input, which in this case is shillings per kilogram. Okay? Which is to say, look, price or cost, whatever, is increasing right now at a rate of 350 shillings per kilogram when we are moving away from 5 kilograms. So why do I specify this last part of at? Well, the price could be some kind of curvy function, right? So the price maybe could look something like this, right? And we want to know, well, I'm currently buying 5, but the price of the 6th or the 7th or the 8th kilogram, right, could be different as we move forward, right? But we're going to assume for the purposes of the tangent line approximation that the price is increasing at whatever the rate that it's currently increasing is, and if it just stays the same, okay, that's what we're going to do. So to do that, all we're going to do is come up with our tangent line formula, which is just 11,500 plus, 350. And to do f of 6, I'm going to put 6 in for x, which is to say, look, I expect that the price of 6 kilograms is going to be the price of 5 kilograms plus, roughly speaking, the average or the instantaneous rate of change at which I'm experiencing at this current expenditure. Okay, which is to say I'm going to take 11,500 plus 350. And I could do the same thing for f of 10 if I just assume that we continue to increase cost at a linear rate, which may not be true, but if I assume that it is true, then I get 11,500 plus 350 times 10 minus 5. Okay? Times 10 minus 5. All right, so that's how we do our tangent line approximation. So any questions on that? All right, does anyone want to take a stab at part C? What do we think is more reliable? Which estimate do we think is more reliable? Someone tell me which one you think is more reliable and why. Noah.
The F of 6 because it's closer to our starting point.
Good. So Noah said it exactly right. I would well, okay, it might not be true, but it's which one do we expect to be more reliable? Probably the nearby approximation, right? Because if I look at 6 here, okay, I can expect the height difference between the tangent line and the function is probably pretty small, right? Probably pretty small. But if I extend this on, okay, it could be at 10 that the price difference between the actual versus the estimate has become potentially large. Okay, it's kind of like these two functions are going along, they have a little bit more time to separate from one another. Okay, so our approximation might not be as good further away. That's the idea. Okay, so that's the tangent line problem. Next up, we're going to look at the next section, which is on concavity, but I want to just quickly ask any final questions about all of this tangent line approximation business? All right, so final comment. You need to memorize this formula, okay? That's something that you just are not going to be able to get around. So do what you have to do. Put it on a note card and put it under your pillow at night so you can absorb it while you're asleep, or something, okay? So we need to memorize this formula moving forward because we're going to come back to tangent line approximation kind of over and over again for the rest of the semester. This is 2.3. Ended up spending a little more time on going back to 2.3 than I was guessing I would, but 2.4 is pretty light. All right, so should we move on to the next section? Yeah, okay, thank you. All right, let's do it. So what's the next section about? The next section is 2.4, which is all about concavity. And we talked a little bit about concavity already, but we're going to make it a lot more specific today. So let's just quickly go through this warm-up problem because I feel like this is instructive to sort of hammer in this notion of the derivative and where it's positive and where it's negative and so on and so forth. Okay, so just because the height of the function is negative doesn't necessarily mean that the derivative is negative, right? Because the derivative represents the steepness of the function, okay? And if I were to draw the tangent line here, it would look something like this, and that's an increasing line which has positive slope. Okay, so I would say f of x is negative, but f prime of x is positive, right? Then at b, I think both are 0, right? Because the height is 0, and also the tangent line would look like a horizontal line, yeah? Horizontal line. Okay? And so on and so forth. So c, I think we're going to be a negative height and a negative slope. D, we got a negative height equals to 0 slope. Y equals to 0. And you're going to notice at b and d, it's like sort of these peaks and valleys where we see our slope being 0, right? Okay, and so on and so forth. I'm just going to go through the rest of these. 0, positive. At F, we've got positive 0. G, we've got positive, negative. Okay, so we can get all the different permutations, all right? The signs of these numbers may have nothing to do with one another, okay? We can be positive and negative. We can be negative and positive. We can be negative, negative, or positive, positive, whatever. Okay, so this is telling us something about whether the function is going up, okay, or whether the function is going down. That's what the derivative tells us, okay, whether the function is increasing or decreasing. And if so, at what rate? What's the steepness? Yes? And the function value itself tells us the height, okay? And now what we're going to do is add one more layer to that description, okay? One more layer to that description, which is going to be done via concavity. So first of all, let's just recall that if f prime is positive, then what can we say about f of x at x naught? We can say that it is increasing, yes? As opposed to f prime negative means we are decreasing. Okay? So questions about that so far before we bring in the third layer? Okay, so the third layer is going to be something like the following. Yes, we have described the height. Yes, we've described whether we're going up or down. But what have we yet to describe is how are we curving, okay? Or how are we bending, okay? So you can think about this in the following way. This curve kind of looks like I'm bending downwards, okay? Do you see what I mean? By which I mean if you were to say, be looking at a road from a top-down perspective, okay? And I was driving on this road, I would be turning my steering wheel to the right. Yes, I'd be turning my steering wheel to the right, meaning that my graph has some curvature to it, okay? And there's sort of two different types of curvature. There's the curvature which looks like this, and then there's the curvature which looks like this, right? And we called those concave down, with the n being here, or versus concave up, with the u being like a concave up shape, right? So now we're going to try to actually quantify that, as opposed to just saying, well, it looks like it's bending down or it looks like it's bending up. Okay. So what can we say? Well, we can take a look at the second derivative. Oh God, two derivatives. Don't panic. The second derivative is just going to be the derivative of the derivative. Okay, no reason we can't find that, because we already established that the derivative is itself a function, and the derivative is changing, and we can ask ourselves, well, how is the derivative changing, right? How is the derivative changing? Well, if the second derivative is positive, then that tells us that our first derivative is increasing, right? Same as before, okay? So this is just a carbon copy of this statement up here, but with one extra apostrophe, right? And then what does that tell us about the actual function itself? Okay, what does that tell us about the actual function itself? Well, let me draw a picture to help you see what I mean. So let's say I did some tangent lines at some random spots, and these are the tangent lines that I saw. One looks like this, and then one looks like this, and then one looks like this, and one looks like this, right? So what's happening? F prime, as we move from left to right, is increasing. Yes? Because this is a negative slope. This is a negative slope, but not as negative. This is a positive slope, and then finally we have a more positive slope. So as we move from left to right, F prime is getting bigger, right? So that's F double prime is positive, means F prime is increasing, means f of x is what? What kind of picture do you think this is going to make when we connect the dots? What kind of graph is that in terms of concavity? In terms of concavity. Yeah, it's concave up, right? Okay, so the second derivative being positive tracks with the first derivative being increasing, which means we see these tangent lines which are becoming more positive as we move from left to right, which is exactly to say that, look, the whole function is sort of bending in this leftwards way, this leftwards kind of way, or upwards kind of way. The way I think about it is like if you were in a car driving, whoops, I guess that's my hood. That's my hood ornament there, okay? So we're moving forwards. Then what are we doing? We're turning the steering wheel to the left. So that's what I mean by like this sort of leftwards turning, okay? So it describes the curvature of our graph, okay? So f prime is increasing, tells us that f of x is concave up. And f of x, f double prime being negative, tells us f prime is decreasing, tells us that f of x is concave down. Okay, concave down. All right, so what do you all think about this second derivative and concavity business? Do we feel okay about that? Okay, are you ready to do some practice? Let's see how much time we have left. Oh, plenty of time. All right, so maybe I want to do a quick table here because I want to show you that again, the positivity or negativity of the second derivative does not necessarily have anything to do with the positivity or the negativity of the first derivative. Okay, so we're going to make a table with several pictures here of what the graph might look like if it satisfies these two conditions. We're going to put it here. So let's do the first one. So first of all, we have f double prime positive. So that tells us that we are concave up. Okay, concave up. And f prime larger than 0 tells us that the function is increasing. So I want to draw a picture of something which is going up from left to right, but also is kind of bending upwards, okay, from left to right. So that picture would look maybe something like this, okay? Something like this would be concave up and increasing as we move from left to right. Okay, and now let's do another one. So f double prime less than 0, we can still be increasing. The only thing we have to do is we still need the function to be going up, but we need to be sort of bending downwards, okay? So I'm just gonna like, imagine that I grabbed with my finger this thing here like a bowstring and I sort of dragged it in this direction, right? Then I could get something which looks more like this, which would be a concave down type of situation. Okay, so this is the graph of something which is increasing. We're still going uphill as we move from left to right, but the curvature is sort of rounded downwards, okay? All right, and then the two final ones, okay, f double prime positive, concave up and decreasing, means we're going to look something like this. And then concave down and decreasing, we're going to look like this. Okay, so these are the sort of four different types of shapes that we can see. And if you had a third dimension on your notebook, you could add in also f being positive or negative. That means whether we're above or below the x-axis, right? Okay, so the four types of shapes that we can have. All right, so we're going to launch into another group exercise, and this is a pretty tough group exercise. So, but I believe that you can all do it. Okay, what we're going to try to do is make 3 different types of graphs. Okay, and I'll warn you all that all of these questions have many different correct answers. Okay, so it's possible you might not draw the exact same thing as your partner, but I want you to identify whether each other's graphs satisfy the criterion which are shown in each of A, B, and C. So do your best to do a little bit of drawing, and Jacob and I will be walking around to help you today. And just raise your hand if you want a little bit of individual attention from either of us.
Single.
So what we got? We've got concave down at 2, and then, so all of these things are at 2. So what does it say? The first thing says F2 is positive, so we should definitely be above the x-axis, so I like that. The second thing says we are increasing, so moving up to
So
this
slope
looks good.
at 0.
And then we should be concave in, so it should be perfect. So that looks perfect, right? Because it looks like part of the letter N, which is in the word down, which is concave in. So, yeah, the other ones are harder, trust me.
Is this just a parabola?
So the 2, right, it's on the inside, right? So that's the separate. On the inside is parentheses. Independent variable goes left and right. So we're actually
Because
X. But what do we say? What do we say? When X is 2, F of 2 is the represents what is going to be just right. And it should be positive. So where should it be? Above the right? So this would be our point. That's what the first thing says. And then the second two things tell us something. How about how
so this is just a.
this tells us that it should be steep. It should be positive, right? And then this number tells us about the current. So the second one is negative. Of course, we take off the going down. It's good because it travels negative. Down, right? So it's concave down, but it's going up. What kind of picture does that look like?
Like that.
Yeah, exactly. All right.
Am I tripping? Is that?
No, I look did.
Because it has the downturn.
Yeah.
All my
Yeah,
things are
exactly.
so
As
bad.
long as it's positive, right? That's why I said there's many, many correct answers. Well, I'd like to move a little bit to the left. So what I would say is something to the tune of like this. Okay, so like namely at 2, okay, or rather like in some small region of 2. You can see it's clearly bending down, it's clearly going up. Yeah. And it's clearly positive.
So you would do.
Well, we are plugging 2 in direct, but so
Or I guess just.
yeah, exactly. So this just says, look, the height of the function is above 0 when x is 2. This is definitely true. Right? We're increasing at this point. Well, increasing is a property which holds generally on intervals, right? But if we say f prime of 2 is larger than 0, what we mean is that we're increasing in some small neighborhood, right? And then f double prime less than 0 again in some small neighborhood for bending down.
And then this is just telling us that.
Well, this one looks great. The second one, what do they say? They tell us f of 1 needs to be positive. Okay? So what that means is that when the x value is 1, rapidly
Because tomorrow.
that's all that that
Oh,
marks,
that's
right?
fun.
And then
I
what
wanna
do
go
they say?
so bad.
F of 0 is less than 0. That means at 0 we need to be going down. And then f prime of 3 is larger than 0. Actually, because the 3
Yes, I saw them on TikTok.
Okay, and they're like, really? And I'm like, okay.
That's so. I'm gonna go try to take
You're on the right track.
They always ask me shit and expect me to say no, but I never say no. Like, I'm always down for it. You're like, you trying to go to Texas? I'm like, okay, when, dude? Like,
I mean, if you get there,
that's what I'm saying.
I would say I'll pay for like her gas.
I just like driving.
Yeah.
I just love driving.
I miss my car. I need to write next year.
Like, for spring break I'm going to Naples to stay at.
My hands are gonna be
I was gonna stay here because I have a bunch of friends here. Like my friend's house, they got like washed out of the ocean. There's no it's like fixed. And now apparently she's like, dude, you need to pull up.
Okay.
That would work.
To the left.
But yeah, like
The steep is to the right. And the height
it's so funny watching your reactions too, because you're asking like the most perfect shit. Yeah, can you take me to the store? And they're like, I didn't expect you to say
Now I know who to ask if I
I'm
ever need to go
literally,
anywhere.
I'm bored, dude. I tell everybody, I just like, me giving rides, I'm like, I was texting like, it's so bad. Like, I'll just do like anything. Like, this is like the other night, my friend's car brought in the battery. I just like pulled up at like midnight to jump in. Like, it's like, I'm everywhere, all the time.
You got them all? Okay, let's check C, because C is the hardest. Okay.
Bro, see, there's the B room from on the roof.
That's so funny.
And then here's like inside the roof on the way up the ladder.
Yeah, I would not try that. I would.
It's spooky up there, dude. I turned off all the lights. It was like it was dark and just ran away and turned my flashlight off. It was like, it scared the shit out of me, dude.
But then I just, so for like this side, it has to match.
So this is your picture?
Yeah.
Of this?
Yeah, whatever.
Okay, so you definitely got this part. F prime is 0, slope is 0, and flat. But we need if F double prime of 2 is less than 0. That means we're concave down. Concave down looks like this, right? But yours looks like the U, which is inward up. Concave up. So I would say
Like,
it needs to maybe
looking through my photos, I just like don't understand how all of this shit happens in one weekend.
That's really cool.
so that we
It's
can be
5:30 a.m. in this video,
But
right?
that's gotta sort of not be
What was I doing though? 5:30 in the morning.
in order to satisfy you kind of need
My new like habit is to take pictures of my photos so out like actual real life. Like I have so many pictures of me, which is like so I take pictures.
So later on,
You just like looking at random couples and
Yes.
let me get a flick. Let me get a
Yes.
No, I always be taking pictures of like everything. I got this is so funny.
Yeah, but
We're all so
last year,
the
second
year all over the house. It even went through the crack right there and it's on the back of it. Like that happened like 3 times that night with different drinks and sauces.
Yeah, you can do that.
Okay, this is what happened. Those girls just like came in and started dancing. And then like I like so it's like that I could finish off a whole line fast with a really funnel a tweet. Which everybody's like looking at me like you're insane. I'm like, bro. So there's
Oh God, that's like
just about like
half.
maybe a little bit more watching quick. I impressed myself. Just watch. I really believe that. Isn't that insane? And I feel like
No. Last time I drank the Thai bottle when I died.
Really?
Yes.
Really?
Let me find
So last time I drank 3 bottles before that. It was known as the wine magazine. I was like already sick. I would chug 2 bottles. That night, I drunk the one part of that night I remember is going up in my friend's back. No
That's
joke.
foul.
I know, that's so bad. That's so bad. Every time somebody starts talking about it, I'm like, no, how do I hear about it? I feel bad for my actions.
I pull up before we went out after mostly gone. Yeah. I had to have my friends in pictures.
No, like, dude, it takes so, like, literally. My friend was like, I think it's people, and I was like, why not? I'm sure that I'll get, like, a bunch. Like,
Tequila, that's what gets me right.
really? I was getting ready for, I was going to send it to my friends for a sorority, and, like, I had, like, 12 shots of tequila, and then 3 teams, and didn't feel fucking
Yeah,
a thing.
I'd be on top
Like,
How am I 4 in the front?
I think we're rocking out. I don't know if rocking out means that we're right, but we're definitely rocking out.
We're shaking head and not happy, or as in
No, like, and it was so funny. It's like, we get done with this set, 4 hours. And like, we're walking out, and we're sitting in the lobby, like the building.
I would say maybe just a little bit, because it looks like it's going in the first place. If we go straight down here,
Wait a minute, are you? And she goes, yeah. And I was like, bro.
So, but the heat is really tight.
I just don't. I'm so tiny. It's so annoying. Like,
Needs to be increasing.
It takes so much for no reason.
And it needs to be
probably like
bending down.
I guess lately I've been pre-gaming just like shots last year.
Don't worry about it. These are
Just take like 2 or something.
I do like
We'll talk about it in
All right. Do we need more time? Okay, let's come back as a group. All right, so like I said, there's like 100 different ways. Actually, there's more than 100. There's infinitely many ways that you could answer all of these problems. But I'm just going to show you some that occur to me, and yours. What you want to identify in terms of yours is whether your graph has the same features as my graph. It might not look the same completely, but it should have the same features, okay? So here I notice, look, f of 2 should be larger than 0. So the very first thing we're going to do is we're going to put a point on the graph, which is above the x-axis. Above the x-axis, that's it. And then the other two things that I need to satisfy are that the graph should be increasing and concave down. Right? Increasing and concave down, which we saw in our table. Increasing and concave down looks like this picture. So all I'm going to do is copy paste it. Okay? And I'm going to make something which looks a little bit like this. Okay? Oops. Yeah, something like that. Looks pretty good. What we need to be true is that in some small region surrounding this point, the graph needs to be going up and bending down. Okay, going up and bending down. So in particular, your graph could even look crazy outside of here, doing all sorts of weird stuff, right? Well, not that weird, but it could be doing some weird things, right? Could even be going up. But the point is that we only really care about what's happening very close to 2. It should be going up and bending down, and the point itself should be above the x-axis. Questions on that one? All right, no questions. So let's talk about the next one. So the next one says we should have, I'm going to start from on the right-hand side, because this is the easiest one to sort of draw, because it just says, look, you should have a point above the x-axis when x is equal to 1. So I'm going to do a point right here. And what do the other things say? Well, f prime of 0 is less than 0 says that we are decreasing. Okay, we are decreasing when the x value is 0, right? And f prime of 3, larger than 0, says that when x is equal to 3, then the slope of the tangent line is a positive number, meaning that we're going up. So we're going down at 0, and we're going up at 3. So one simple way to connect these would be to draw something which looks like this. Okay, something which looks like that. But here's another way you could have drawn it if you wanted to. You could have drawn something like this. Who knows? Whatever. But these two graphs have the same features in that they're above the x-axis when the x value is 1. When the x value is 0, they're going down. And when the x value is 3, they're going up. Right? Those are the 3 criterion which we have to satisfy here. Any questions on that one? Okay, then let's talk about the last one. Did we think the last one was the hardest? Yeah, I think the last one was the hardest. So what do they say? They want us to be concave down at -2, concave up at 2, and the tangent line needs to be horizontal at 0. But otherwise, they don't tell us anything about the height of the function, do they? So I'm just going to pick a random height for 0. I don't know, maybe here. And I know that the tangent line needs to be kind of flat, right? Tangent line needs to be sort of flat at this point, right? And what else do we need? We need concave down to the left. Okay, concave down. Well, the choices for concave down look like this, or like this. Those are the two options for concave down. And then to the right, so I'm going to put one of those here. And then to the right, I'm going to put something which looks concave up. So concave up looks like either like this or like this. So I'm just going to look for a good way to connect these two. It looks like this one would connect pretty well with this one. So that's what I'm going to do. So I could draw a picture which looks like, okay, that's not very good. You could draw a picture which looks like this. Okay, and we have to flatten out at 0, but then we can be concave up after that. So the point here is that as I come along, I'm concave down because I'm bending downwards, and then I'm concave up, I'm bending upwards, and right at 0, my tangent line is actually a horizontal line. Okay, it's actually a horizontal line. Okay, so that's an example of something that you could have drawn. Another one, actually the one that I initially drew, I was like, okay, how the hell do I do this? What I ended up doing was something which looked like this. So concave down at -2, and then I did it like that, and then I just connected it in the same way to the right. That's what I initially drew before I realized that Olivia is way smarter than me and drew something that looks like that. Okay, so how do we feel about that last one? A little bit better now that we've seen it worked out? Okay, let's have some thumbs. Thumbs up if you feel like you could have done this problem on the exam or on the quiz if we had one on Thursday. And thumbs up, thumbs down if you feel like I wouldn't have done so hot on that quiz. Raise them nice and high, please. Real high. Okay. Yeah, it's a tough exercise, okay? This is what we call a high cognitive task, okay? It's tricky because you got to be a little bit creative with it, which we usually don't ask you to be that creative in business calc, but pretty fun example, I think. All right, well, let's see some more stuff. I'm going to talk for a little bit here. So let's, I want to go over this problem here. Okay, because this is another fun problem. What do they tell us? They give us some information and they ask us to make a conclusion about f of 6. So what's the information we have? They say f of 3 is 15. So here's 3. We're at 15. They tell us f prime of 3 is -3. So we're going down. And they tell us, furthermore, that f double prime is positive for x larger than 3. What does that tell us? That tells us everywhere to the right of 3, the function needs to be concave up. Okay? Needs to be concave up. So f of 3 is 15, f prime of 3 is -3, and the function needs to be concave up. Okay, so what could this possibly look like? Is it possible for f of 6 to take on these 3 values? Let's check. Well, let's put 6 here, and let's put 10 on here. Okay, here's 10. Well, what is this really testing? Okay, so this is testing whether we understand concavity, which basically says, look, the first derivative is increasing to the right. Okay, so first derivative is increasing. Okay, so that means that my graph has to lie sort of to the right of this line, because this line has slope m equals to -3. In order for me to be concave up, I have to be bending away from it, right? I have to be bending away from this line. So in particular, any points which lie underneath this line are going to be impossible for the function to attain, because it cannot decrease faster than f prime of 3 equals to -3. It can't decrease faster because the first derivative is increasing, not decreasing. Okay, so let's see which one of these is possible. Well, if I wanted to find the actual point on this line, which corresponds with x equals to 6, it's probably going to be a positive point, I'm guessing. Let's find the equation of this line. Well, the equation of that line is, guess what? The equation of the tangent line. So this line has equation t of x equals to 15 minus 3 times x minus 3. And let's plug in t of 6, which will give us the height of this point here. So if I do that, I get 15 minus 3 times x minus 3, or sorry, 6 minus 3, which is equal to 15 minus 9, yes? Which is equal to 6. Okay, so this point here has height 6. And I know that my function, whatever it's doing, it needs to be bending away, right? It needs to be bending away because it's concave up. So, can I accomplish a height of this purple curve being lower than this while still bending away from this line? No, I can't, right? I would have to sort of come back down, and this would cause me to violate this concavity criterion. Okay? So, 3, not possible. How about 6? Can I get 6 as an answer? What do we think? Or you feel like this problem is way too hard? Yeah, Alex. Oh, you're saying yes, you think the question is way too hard. Thank you. Okay, well, let me ask you, in order to get to 6, okay, the best possible way would be to do a straight line. Is a straight line concave up? No, it doesn't have any concavity. Concave up, we need to have some curvature away. So if I have some curvature away, there's no way that I can actually get down to 6. I'd have to take an exactly straight path, or else I would need to be concave down at some point. Okay, but I know my function is concave up to the right, so 6 is not attainable either. But 10 is okay, because we could put 10, I could rescale this a little bit so it's more realistic. We can put 10 here, and there could be a concave up function, i.e. a function which peels away from the tangent line in this kind of a fashion, which goes through 10. That's no problem. Okay, because 10 is larger than 6, right? Okay, so a bit of a tricky problem there. But what it's supposed to illustrate, okay, what it is supposed to illustrate is, what is this concavity business all about? It's about this sort of curving away from the tangent line, okay, in a certain direction, okay? So these two pictures are on top, concave up, on bottom, concave down. In either case, it tells you whether your tangent line approximation is an underestimate or an overestimate, okay? Tells you whether your tangent line approximation is an underestimate or an overestimate. Okay, but that's maybe a little bit high on the theory side of things. Do we have any questions on that one? Okay, we got 5 minutes left. With that, I want to tell you, we're going to skip problem 4, and I want to tell you about one more concept to finish up 2.4, and that is what is concavity with tables, okay? So, if I have a table of information, how do I tell whether the function is concave up or concave down? Okay? How do I tell whether the function is concave up or concave down if I just have a table of values? Because I don't have the graph. I can't see whether it looks like it's bending down or whether it looks like it's bending up, okay? So there's sort of two options that you could take here. What you could try to do is try to graph this information. But I would sort of recommend against that because your graph is probably not going to look perfect, okay? And you could sort of be led astray by trying to make your own graph of this thing, okay? So what we want to instead describe is what does the second derivative being positive really mean? What it really means is that the slope is increasing as we move from left to right, okay? So let me visualize that for you again. Slope is increasing as we move from left to right, means we're concave up. Slope is increasing is going to be an easier thing to check with a table, okay? Easier thing to check with a table. All I need to ask myself is, look, I want to look for an accelerating rate of change, okay? Accelerating rate of change, meaning that the slope from 2 to 4, okay, is like 2, right? If we're going over by 1 each time. So let's say we go 1, 2, 3, 4, 5, 6. I'm going to look at the slope between each data point. The slope here is 2. The slope here is 4. The slope here is 8. The slope here is 16. And then the slope here is 32. So if I drew some tangent lines with slope 2 and then 4 and then 8 and then 16 and then 32, what would it look like? It would look like here's 2, here's 4, here's 8, here's 16, right? You can see that it's clearly going to give me a profile which is concave up, right? Because the first derivative is increasing, okay? The slope is increasing. So this is what we look for in a table, is accelerating rate of change. Or if we want to look for concave down, we want decelerating or negatively accelerating rate of change, okay? So what could that look like? I showed you accelerating. Here's decelerating. From here to here, we went up by 58. Here to here, we went up by 20. Here to here, we went up by 10, 5, and then 1. So the slopes here look like incredibly steep at first, and then less steep, and then less steep, and then less steep, and then less steep, right? What is that telling us? Sorry, what did I say?
95 to 96.
Yeah, sorry, 95 to 96. Sorry, thank you. So if we go up by 1, thank you. So yes, up, and then up, but less so, and then up, but less so, up, but less so. What kind of picture is that? It's concave down, right? So you look for these types of patterns in the numbers in the table. So quickly, this example, we see from here to here, what do we do? Up by 1, up by 2, up by 3, up by 5, up by 7. What sign do we expect f double prime to have going from left to right for this region? Positive or negative?
Positive.
Positive, because we're concave up. Good, I like that unison answer, thank you. All right, let's close there for today.